Hello CTMers, and welcome to the lesson on 3.5. Can be found on these pages. And if you're in my class, again, read this and make sure you do what it says there. Have it ready for the due date. Some vocabulary for this lesson. You can see all these things here. You should know these words or phrases by the time we're done with this lesson. So let's get started, and again, make sure that you use extra examples in your book. Not quite as many for this one as the last one. There are actually 7 examples in your book. We'll do a few together here. Extra examples as well. So let's get started on this. 3.5 note, symbolic arguments. Make sure you write that at the top of your paper. And we need to know when an argument is valid and when it's invalid, or we also call that a fallacy. So an argument is valid. You need to start off by saying this. An argument is valid when... Let's fill in the rest of this here. When its conclusion necessarily follows. So has to follow. Necessarily follows from a given set of premises. Not really sure. Premises or premises, how we would say that. I'll have to look that up. But premises or premises. So it has to be true based on these given premises. Argument is valid or invalid or a fallacy when, well, it's pretty much the same except when it does not follow from a given set of premises. So when the conclusion does not, or doesn't, you could say, does not follow from a given set of premises. And I'm just going to say premises for plural. You can call the vocab cops on me if I got that wrong. When its conclusion necessarily follows. So this one, it does follow. This one does not follow from a given set of premises. Alright, so pretty basic there. So now let's actually look at some logical arguments and see if what we have would or would not follow. So let's start off with this. And you can notice, yes, we got pigs flying, scarecrows dancing over here. Here's the situation, or here's the logical argument that I'm trying to make. If pigs can fly, then scarecrows can dance. If pigs can fly, then scarecrows can dance. That's my first statement. My second statement is going to be this: scarecrows cannot dance. And we'll see again here that a lot of the stuff we've been doing in this chapter, there's a lot of similarities between just like basic arithmetic and the notation we use here. So I'm kind of saying I'm adding, in a sense, this first statement and this first statement to get this. So this plus this, in a sense, equals this. That's what I'm trying to figure out is true. This is a new symbol for us. 3 little dots that make up essentially a small equilateral triangle. This means therefore. So therefore, pigs cannot fly. That's what I need to figure out, if it's valid or invalid. And let's make a little note of this just off to the side here. So that just means therefore. If you see that, that means therefore. Okay, so let's work this out. Let's write this in symbols like we've been practicing these last few lessons here. So let's say P is the statement pigs can fly. Pigs can fly. Q is the statement scarecrows can dance. So now if we take this, what I had up here in words, and now put it into symbols, it would look like this instead. So in symbols, we would have something that looks like this now. We'd have P implies Q. That's if pigs can fly, then scarecrows can dance. P implies Q. And we also have not Q. We have scarecrows cannot dance. And then therefore we say pigs cannot fly. So pigs cannot fly. I should undo that. You know what, I'm going to write this whole thing beneath so I have some room for a truth table over here. So I would just say P implies Q, not Q, therefore not P. So that's what it is in symbols. I haven't decided if it's true or not yet, if it's a valid argument or not. So now that's what I'm going to do over here. So now I'm going to make up a truth table, and I'm going to use my line tools here again to make a nice looking one. And you've got the blue lines on your paper if you're taking notes on this. So let's say that's for P, that's for Q, and then I'm just going to leave the rest of this all blank for now, or no extra rows here. I might add some rows in a lighter color to make sure it's easier to follow. But let's say we have here, this is P now, this is Q. So just like before, we've got true, true, false, false, and true, false, true, false. And now what is this saying here? Well, I'm saying this, I'm going to assume is one statement, one whole thing, and this. So I'm saying this and this being true would imply the truth of this. So what I'm going to put in here, and this sort of idea or this sort of way of doing things is going to work for all these ones that we're doing here in this lesson. We're saying P implies Q, and this is just a bracket. It's just another way to write parentheses. It's just a way to keep this set of parentheses distinct from this set of parentheses, but it just means the same thing. So it's just another set of parentheses. So I kind of have an inner parentheses here, and this is an outer parentheses here. So I would want to do this, the inner parentheses first, P implies Q, and I would want to also check not Q. Okay, so this all goes together. I'm saying this and this being true. Does that have to imply that the conclusion that we made down here, does it have to imply that that is true? So does this and this imply that not P is true? So let's check this out and let's see what we got. So this, I'm going to say, I'm going to do P implies Q all at once together because I already have my P row and my Q row here. I can look at that easily and just plug that in. I don't have to replug in P all here and replug in Q all here. So I'll do that first, and then I'll do this second. I'm going to color code things as we go to make things a little easier to see what's going on here. So P implies Q. Remember, you look for the one where you'd have a P as true and Q as false. That's the only one that ends up being false. The rest, we say the rest are all true. So this whole row here, P implies Q, that whole idea, this is true, false, true, true. That's my first thing I do. And then not Q, just take Q and negate all that, flip it around. So false, true, false, true. Now I can look at this. I'll use, how about I go with this kind of purplish color. I'll say this is my third thing now. Now I want to finish this outer set of parentheses. So true, false, are both of these true? This and this being true. There's only one where both of them are true. That's that one right there. And so the rest, we have false, false, false. They both have to be true for and to be true. And we look at not P, this would come fourth. So not P, we take our P and negate that. We've got false, false, true, true. Okay, so now I look at 3 and I look at 4. That's now what I'm comparing to fill in this last row. So this is my final answer, you might say. I'll do that in black. It's kind of getting, the colors are getting darker and darker as I get to my final answer. So this is going to be, well, is this going to be true? We look for the true to false again. So that's does this whole thing, a whole set of parentheses, does that imply that not P is going to happen? So I don't see any true to false. I see false to true, false to false, false to false, and I see a true to true. So all of these are T's. All of these are true. We did this last. So this is my final answer in a truth table form. Now, what did we learn from the last lesson? What is that called? If they're all true, that's called a tautology. So this is a tautology. And if you have a tautology, that means it's always true. That means the argument is valid. That is a valid argument. So a tautology, and so that's what that is. So we would say that this is valid. This is a tautology, so it's a valid argument right there. Alright, let's move on to another example. And you may have looked at this and said, well, Mr. Wagner, I looked at this and that sure seemed like it was going to be true without doing this whole truth table thing. P implies Q, not Q is true, so therefore not P would have to be true. If this top stuff is going to work out, that has to work out. And there is a law that actually allows us to do that without doing the whole truth table. You may notice that this is kind of like the contrapositive of this statement, and that's the law. There's called a law of contraposition. There's a law of some other things too. So let's do that here. There's a standard forms of arguments. So there are 4 standard forms of arguments that are valid and 2 that are invalid. Let's write all these things down here. So one of them, I'll use some different colors here to just make things stand out a little nicer. One of them is the law of detachment. This is the most basic one. The law of detachment. Sometimes they call this, I'll bring up my site here. Sometimes you'll hear it called modus ponens, the law of detachment. This is just another, you're saying in Latin, it's a Latin phrase, the way that affirms by affirming. So this is the same thing as what we're talking about here with the law of detachment. So we're going to remember law of detachment, not modus ponens. This says that P implies Q if that's true, and if P is true, so the first part is true, if this was true and this was true, that would mean therefore that Q would have to follow from that. So this Frisbee, I'll get to that in a second and show you why I have that drawn on there. We're going to do some verbal examples here. So let's say that's the law of detachment. Let's talk about, I already mentioned this one, the law of contraposition. The law of contraposition deals with contrapositives. We learned about those in the previous lesson. So, sorry, not law of contrapositive, law of contraposition. Contraposition, there we go. Says that if P implies Q is true and not Q is true, that means therefore not P is true. So that's the law of contraposition. There's also something called the law of syllogism. Law of syllogism. And you may recognize that word from your geometry class. It's probably been a while since you heard that word, but the law of syllogism says that if you have something like this, P implies Q being true, and then another thing like Q implies R being true as well, that means you could go right from the first one and say that the last one is true. You could say therefore P implies R is also a true statement. And one other one that is valid, and do this one in red, the disjunctive syllogism. Disjunctive syllogism. So disjunction, we think of the word or with that. Disjunctive syllogism is this. You have P or Q being true, and we would say one of those is not true. We'll call the one that's not true P. So if this were true and this were true, well, that would mean that Q would have to be true, because one of these two, at least one of these two, has to be true. If it's not P being true, then Q would have to be the one that would be true. So these are all valid arguments. And then down here I'm going to have some invalid arguments. So I'll go with a different color here. So let's say use purple for this one, fallacy. So a fallacy is an invalid argument. Another way to say that word, fallacy of the converse. And in our previous lesson 3.4 we saw that if you had a converse and inverse, they're logically equivalent. If you had the conditional and the contrapositive, those are also logically equivalent. So a fallacy of the converse, I think if the converse is false, so is the inverse. That's also going to be false, and we'll get to that in the next ones. But the fallacy of the converse says this, and if you listen carefully, a lot of people will try to make arguments like this, and it just doesn't follow. They would say like P implies Q, and the second thing's true, therefore the first thing must have been true as well. That is not a true statement. So this is a fallacy. This is something that is invalid. This is not an argument that works. And let's go with orange. So the fallacy of the converse, and you also have the fallacy of the inverse. So this says P implies Q if that's a true statement, and not P is true, therefore not Q is true. Some people will try to say that, but again, this is a fallacy. This doesn't work. Just because P implies Q is true and not P is true, it doesn't mean that not Q has to be true. So I want to show you, just for fun, a little clip about ultimate frisbee, and then I'll use that as an example to help further explain these. And hey, how you doing? I just want you to see my reaction to this thing. Bring that back up.
Splitter is actually ideal for ultimate. I mean, it's cool, and there's very little wind, and that's what any ultimate player wants, especially if you're on the offensive side.
Nice catch, nice catch.
That was a good catch.
That was great.
What is he doing?
Down it goes.
No way.
Can he get it? And
No.
oh, he bolted it in! Oh my gosh! Wow.
Okay. Just nuts. That is a crazy catch. I love me some ultimate frisbee. And using that, here's a picture of an ultimate disc. Let's say it is Saturday. I like to play ultimate frisbee on Saturday mornings. I kind of play with a group around here where I live. And so it is Saturday is going to be P. So I'll just draw this. You don't have to write this part down. I'll just write this in green over here. So don't write this down over here, but just so you know what I'm talking about. So let's say P it is Saturday, and let's say Q is I play ultimate frisbee. So you can just call it ultimate. That's what most people in the ultimate community would call it. So it is Saturday, I play ultimate. Let's say this is a true statement. So P implies Q. So if P implies Q and then P is true, it is Saturday, therefore, by the law of attachment, yeah, I'm going to play ultimate. If you said the law of contraposition and use this, you could say that if it is Saturday, then I play ultimate if that's true, and if I did not play ultimate, then it would not be Saturday. That would follow from the law of contraposition. Law of syllogism, this one I'm going to show you a different video to kind of help you determine that, but the P or R here now, P or R, not P being true, that would mean Q would have to be true. So either it is Saturday or I play ultimate. It's not Saturday, then I would play ultimate if one of those two things were true. But the fallacies here, why would this not work? This helps explain this a little better, I think. So if P implies Q is true, so it is Saturday, therefore I play ultimate. It is Saturday, if Saturday, then I play ultimate. I play ultimate. Well, sometimes I end up playing on Tuesdays too, or a different day of the week. Just because I played ultimate doesn't mean it has to be Saturday. So P does not necessarily follow from this being true. And the same sort of idea here for the fallacy of the inverse. So if this is true, but it's not Saturday, well, it doesn't mean I didn't play ultimate. It could be another day of the week where I played ultimate. So the law of syllogism, let me show you another video to go along with that, but I'm going to show you that later after a further example that we do. So let's do a second example, and we'll get to the law of syllogism in our third example. So let's say that this is our argument. So if you pass general chemistry, then you may take, and if your line goes over and spills over to the second line, give a little indent here so that I know it's not a new premise. This all belongs with the same premise. So if you pass general chemistry, then you may take organic chemistry. It's kind of like the next level of chemistry. Okay, and if you pass general chemistry, then you may take organic chemistry. And we'll say our second premise is that you pass general chemistry. So let's say that actually happened. You pass general chemistry. And my argument's going to say that, well, therefore, let's see if this is true. Therefore, you may take organic chemistry. So you may look at that and say, well, I looked at these laws over here, I already know which one goes along with that. I do want to get some practice though with, again, putting this into symbols. I had meant to do red before when I did this, so let's go and do that. So with my P's and Q's, I will say that P is you pass general chemistry. That's one simple statement in there. You pass general chemistry. And then statement Q is that you may take organic chemistry. Alright, now we have our what we need for the symbolic part, so let's write down in symbols now what would this look like. In symbols we would have, we've got P. If you pass general chemistry, then you may take organic chemistry. We've got P implies Q. And you pass general chemistry, so that's just P. And they say that, therefore, you may take organic chemistry, so they say, therefore, Q. Look at this, P implies Q, P is true, therefore Q is true. Is that one of my valid arguments? Yes, it is. That's the law of detachment right here. So this one, if you were asked, is this a true or a valid argument, you would say, yeah, this is valid. And if you had to give a reason, you would say, by the law of detachment. Now, notice, I did not draw a truth table. I was going to say a tooth table. A truth table. Could I draw a truth table if I wasn't seeing this? Yeah, it's going to be a lot more work, a lot of unnecessary work in this case, because the law of detachment just tells you that right away. This is logical, this is a valid argument that we can use at any time if we have something that looks like this. So that is how that one's done. Let's do one here where we have the law of syllogism, and lots of interesting pictures here that we'll get to in just a moment. So let's say we have this. If you're Superman, then you can fly fast. And if you can fly fast, then, well, you end up like this guy. Nobody ever talks about this, but Superman, he deals with this all the time, I'm sure. Just, I don't know, he just never shares it because maybe he's embarrassed by it. But you end up like this guy. You have bugs splattered all over your face. So then bugs will splatter on your face. So let's say those two premises are true. Therefore, well, let's see if this follows from what we said there. If you're Superman, this is my supposed conclusion. If you're Superman, then bugs will splatter on your face. Okay, so again, let's write this in symbols like we did before. You may look at this and you may already know what law this is. I've given you, I kind of already have told you what this one was going to be. But in symbols, what would this look like? Well, let's say, and just so we don't think I always have to write P, Q, and R, let's use some different letters on this one. So let's say S is this. S is going to be that you are, or you're, Superman. And let's say that fly fast, we'll call that F, because we'll use F for fly. Sometimes that's a good way to do things. So I went with S for Superman, I went with F for the fly fast part. So we'll say that you can fly fast, especially if you have more than two premises. Then labeling them with letters that match up with something in the statement itself can be more and more helpful the more and more things you get. So then bugs will splatter on your face. We'll use B for bugs. So bugs will splatter on your face. Bugs will splatter on your face. So we have S, F, and B instead of P, Q, and R. I decided to go with some different letters just so we get used to just seeing that. So now in symbols, or I should have said let this be true, but we can keep that like that. Alright, so in symbols we're going to have my argument now becomes S, you're Superman, then you can fly fast. S implies F. The second premise, if you can fly fast, that's F implies, then bugs will splatter on your face, implies B, and then the final conclusion statement there is if you're Superman, then bugs will splatter on your face. S implies B. Is this a valid argument? Well, let's go back to the four we had. If it's not one of the four we had, and it's not one of the fallacies, it might still be true. We would have to do a truth table then. But if it is one of the ones that we have back here, which it is, it's the law of syllogism, just with different letters now. If it's one of those ones, then we don't have to do a truth table. We can just say right away what it is. So this one is valid. And if you had to give a reason, you would say it's valid by the law of syllogism. So maybe superhero business isn't all it's cracked up to be. This guy, he had dreams of being a superhero when he was younger, and I think he grew up to be this guy. He wanted to become the Fist of Goodness. So let's see a little commercial about the Fist of Goodness, and it actually really, really well describes the law of syllogism. So
when you pay too much for cable, you feel powerless. When you feel powerless, you want to take the power back. When you want to take the power back, you take karate. When you take karate, you want to use your karate. When you want to use your karate, you become the Fist of Goodness. When you become the Fist of Goodness, you run along rooftops. And when you run along rooftops, you fall into a dinner party. Don't fall into a dinner party. Get rid of cable and upgrade to DirecTV. Call 1-800-DirecTV.
Okay, so that showed the law of syllogism just kind of in an extended way. You pay too much for cable, you're powerless. You're powerless, you want to take the power back. Power back goes to karate. Karate means you want to use your karate. Use your karate, you become the Fist of Goodness. The Fist of Goodness means you run along rooftops, and then that all means you fall into a dinner party. So I could say that if you started off by paying too much for cable, you could go all the way to the end, or any one of those arguments in between, and say that the first thing would imply the very last thing, that if you pay too much for cable, then you fall into a dinner party. A great, funny example of the law of syllogism there. Let's do our next example. So Tom and Jerry, if you recognize those guys, that's who that is. We're going to have a little cat and mouse example right here. let's say that this is how this one will go. So if, and this one I'm not going to write in that kind of addition, in a sense, addition format where I have this plus this in a sense equals that. I'm just going to write it out in a paragraph. So we need to know how to do one like this too. If the cat is in the room, then the mice are hiding. Let's also say the mice are hiding. Therefore, the cat is in the room. Alright, well, is this true or not? Let's come up in symbols with what we could say. I'll go back to my P and Q here. I could use C and M for cat and mice if I wanted to, but I'll just go back to the P and the Q. So let's say P is the cat is in the room. Let's say Q is the mice are hiding. So we've got now what we need for our symbolic form. Symbolic argument here would become, now this one we have to do maybe just a little more thinking than what we had before, because before we had this plus this in a sense equals this. Now we have to take our paragraph and kind of break it down a little bit more. But if the cat is in the room, then the mice are hiding. That's the first premise. That would be P implies Q. And then the second premise, the mice are hiding. That would be Q. So that and that, they say means, or this paragraph say it means that the cat is in the room, therefore P. Well, is that true? We could make a truth table and figure it out from that, but let's look at that and see if there's one of those shortcuts, one of those laws or fallacies that would help us determine this one without the truth table. So P implies Q, and the Q, that part is second, or that part is being true. Does that mean P had to be true for this to work? Well, no. That's the converse. Switching that around, that's the fallacy of the converse. That's this one right here. So P implies Q. Q being true doesn't mean that P had to be true. The mice could be hiding for another reason. They could be hiding because maybe there's a scary dog in the room, or maybe there's a bunch of mouse traps out and they're smart mice and they know they can't go out because they're gonna die. I don't know. Maybe there's another reason. It doesn't have to be because the cat's not there or whatever. So this one, this is invalid by fallacy of the converse. Fallacy of the converse. And we got one more example. This one we're going to have 3 premises now instead. So sometimes you have more than 2, and this one we need to see if this will work out with 3. We need to know how to do that as well. So let's say now that these are our 3 premises. If you like to travel, there we go. If you like to travel, then you like one of my favorite TV shows. I don't watch too much TV these days, but I'd like to start watching this again once I have a little more time. Then you like The Amazing Race. Great show. The winners get $1 million. Pretty cool, traveling in teams of 2 around the world. If you, let's say this is our second premise, if you never leave the house, if you never leave the house, then you don't like to travel. So maybe you're like this guy, you're a couch potato and you just sit on the couch all day, every day, and you never give up, and you never leave the house. Somehow you get money for never leaving the house. Maybe you have a business at home or something, and you just stay at home all day, you don't like to travel. So let's say you're maybe this guy. And then a third premise we'll say is you like to travel. Or you never leave the house. So my three, let's see, that looks like a letter almost. There we go. And my conclusion here, we're going to see if this is true. You like The Amazing Race, or you don't like to travel. So we've got three premises, we've got our conclusion. Let's write down our three premises. I'm going to use letters that match up with what's here instead of P, Q, and R. I could use P, Q, and R, but I'm going to go with T for travel. I'm going to go with A for Amazing Race, and I'm going to go with H for never leaving the house. So T is going to be you like to travel. You like to travel. A will be like you. It won't be like, it will be you like The Amazing Race. And H will be you never leave the house. You never leave the house. I'm going to need all this room down here for my symbolic argument. I'm going to make a truth table with this one because this is not going to be one of one more there, but it's not going to be one of these because we've got three premises. These all just have two premises. We may be able to think about this and logically say, okay, yeah, that's going to be true, but we're going to draw a truth table to go along with these to verify what we think might be true, what we think might be the case. So in symbols, we'll do that over here. In symbols, let me use, it'll stand out a little better, I'll use blue over here. One more. So in symbols, I would have this being the same thing. So if you like to travel, then you like The Amazing Race. T implies A. If you never leave the house, that would be H. Implies you don't like to travel, so you not T. And you also have you like to travel, so that's T. Or, here's my or symbol, or you never leave the house, H. T or H. And therefore, we're saying that it's either A or not T. Well, I look at this, and this does make sense to me because T or H being true would mean this or this would be true, and that would imply that that or that would be true. But let's do the table here and verify that what I think is true is actually going to hold, that it's going to be a tautology, that it's going to work out in every case. Okay, and let's see here. I'm going to have to draw a little small here. So this is going to be my T, this will be my H, and this, or my T here, my A here, my H here. I'm going to put an extra column right now, right here for not T. I'll show you why, or we'll see why that is in a second. So T, A, H, not T. Make my horizontal line here. And then I'm going to leave this all blank. This is our whole argument going together right here. So this, we'll put a, yeah, there we go. Put a T here, A here, H here, and not T here. So this is going to be, use the lowercase letters for the premises, use uppercase, T's and F's true, false, true, false. You know what? I'm going to add yellow lines because this is going to get, there's going to be a lot here. Let me add some yellow lines in here just to make sure things stay. Nope, that's not yellow. Yellow. There we go. But I want that a little higher here. Okay, so there we go. That'll be one row. I'm going to add 8 rows. You've got the blue lines on your paper to help you keep things straight. 2, 3, 4. I can count. All right, 5, 6, 7, and 8. I'm thinking about Sesame Street now with the count. Growing up watching that. 1, 2, 3, 4. That ain't what I want. I want black. There we go. Boom. So that was supposed to be not T. Notice my T's, I put a little curl at the end so they don't look like plus signs. I would highly recommend you do the same thing with yours. So this is going to be true, true, oops, true, true, false, 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 and then this one I'm just leaving for my order down here, the order I'm going to do things in. So just like before with P, Q, and R, we do 4 true, 4 false. Then 2, 2, 2, and 2, and then every other like that. That didn't change at all. So true, true, false, false, and then true, false, true, false, true, false, true, false. And I noticed in my symbolic argument that I had not T, and that's going to show up twice. So there's no other nots here, so I just made one for that only, for not T only. So I'm just taking T and negating all those things, changing those around. This will be helpful for me later on. Okay, so now I'm saying all 3 of these things come first. Do all these 3 things first, and then therefore this is supposed to be true. That's supposed to follow from that. So I'm going to have an outer set of parentheses and then kind of 3 sets of inner parentheses. I'm going to say this is one thing, T implies A is one thing, and this. So this and this, H implies not T, and this, and T or H. Now in my second parentheses there, this all is supposed to imply, if this is a valid argument, this and this being true is supposed to imply that this is also going to follow from that. That A or not T is supposed to work based on that. So could I rewrite the T and the A all here? Yeah, but it's already over here. So I'm just going to do this and this and this. I'm going to do those things first. So I'll use lighter colors and kind of work my way up to darker colors as I get closer and closer to this. This is going to be the last thing I do. This big set of parentheses here implies this smaller one here. I'm going to see if that's true. So my final answer, this is where I'm going. This is what I'm going to do last. Right here is what I'm going to do last. And if that's all trues, then I know that this is a valid argument. So let's start with, go with green here. Let's start with this one. And let's start with this one and this one. So these 3 things I'm going to figure out first. And then I'm going to figure out, well, if this one is true or false, whatever. And is the and work? Does the and work? I'm going to do that one afterwards and go from there and figure out this one here. So let's see. T implies A. So I'm look for the T's in the first column and then the F's in the second column. That's the only ones that are kind of weird, that are kind of different. It's the only ones that are false. So if you have a T to an F here, you have a T to an F here. The rest are not like that. So the only one we have the conditional being false is when the first part's true, the second part's false. The rest of them are going to be T's. The rest are going to be trues. So true, 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 true. Same sort of thing with H implies not T. So I wrote my not T right here to make it easier. Look for the T's to F's. Those are the false ones. Any other T's to F's? Here's one. So here's another false one. T to F, nowhere else. So the rest of these are going to be true, 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 and true. And then T or H, just one or both can be true, but you only need one. So at least one being true, the only one or ones where I see at least one not being true would be this row right here, the 6th row, and the 8th row. So right here I would say this is false, and I would say that this is false. The rest would be true. True, 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 and true. Okay, so we've got all that. And then if you remember the associative property of addition, of multiplication, this kind of is like that. We can do either this, the first row to the first column to the second column, and do that and first, or we could do the second one to the third one first. I'm just going to go in order and move left to right. So I'm going to say that now. I'm going to call this, I don't know if that's technically any darker than that kind of greenish color, but go to this. So 4, is this and this being true? Well, they both have to be true if that's going to be a true statement. So this one, they're both true. And then these last 4, they're all both true as well. The rest of these are false, 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 false. Okay, and now we got that. And now we're taking this. I'm taking this one, 4, and we're going to compare it with 3, because it's kind of like I was saying, okay, I'll add another parentheses here. I just did this all together. I did this and this. Was that true? That's row 4. Now I want to say this all together and this part. Is that a true statement? So let's check this one compared to this one. And let's see, we're looking for true and true. So this one is true and true. And this one is true and true. And this one is true and true. And then the rest of those, it's like it's going to be, none of the rest will work, so the rest will be false. Alright, so I've got that row, or that column now successfully there. So now I want to take that, and let me do this row, or this column now too. A or not T. A or not T. So take a look back here. Here's A, here's not T. Just one of them has to be true. They can both be true, but at least one. And there's only this one and this one where there's not at least one being true. So that's going to be false there, and that's going to be false there. So just third row, fourth row, they're false. The rest are going to be true. True, true, true. We did this. 6th. Now we want to compare the last couple I just did there. So I want to compare now this one, the 5th one I did, with the 6th one that I did. So I'm using some darker colors now. I want to compare these 2 columns now to get this final answer. So now remember what I look for. This is the implies arrow, the conditional. So I'm looking for anything where it would be true first and then false second. That would be a false statement. So I look here. Here's a true, but that's true. Here's a true, but that's true. Here's a true, but that's true. So all of these have to be true. So this is going to be true, 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 and true 8 times. And that's exactly what we wanted to happen. We wanted a tautology if it was going to be valid. So I'm going to just do this off to the side. This is a tautology, which means that the whole argument was a valid argument. If they end up all being true, that means this has to be a true thing. Just kind of like we thought intuitively based on what was here. We thought it was going to be valid. We verified it with the truth table. So you can always fall back on the truth tables. If there's not one of the laws that you learned, then you have to do the truth table to verify it. But if it's one of these laws that we learned, then you could use one of those as kind of a shortcut with this lesson. If you have any questions, please ask in class when we have some time to go over things. Otherwise, I hope, oh, we didn't need that page. That's from an old one. So we end here. We don't have to do any more. We're not going to do any more there. So hopefully that helped. And again, let me know if you have any questions in class. I'll see you guys later.